We're going to have our next talk, which is going to be from Matthias Saba, and he's going to talk about metasurfaces, top metamaterials, topological origin, polarization effect, and gyroid materials.
Thanks very much. I'd also like to thank the organizers in the Newton Institute, of course, and especially Adil and Simon for inviting me to give a presentation here, even though, as you can see, I'm clearly off topic in this conference. So if you don't enjoy it, blame them. If you do enjoy it, it's me. I'd also like to thank my co-authors, of course, which you can find in this publication. Special thanks to Jamie, who, well, I'm a theorist. He did the experimental work, all the optical characterization and fabrication of these materials. So my excuse is that I'm going to talk about at least geometry and a little bit of functional materials that are made by self-assembly. And also thanks to An Shang for giving a nice introduction to block copolymer self-assembly in the morning. So with that, I'd like to get started. This is the gyroid. Who has seen this structure before in the audience? Quite a few people. Great, excellent. So I don't have to introduce it too much in this audience. I'd just like to mention that for the purposes, what I want to do with this is I want to build, or what we're doing actually experimentally as well, we're building an optical material with this structure. So essentially what I would like to draw your attention to are two properties of the gyroid. And of course, if you know it, you probably know those. It's a cubic structure. I've represented that by a cube, octahedron. It has cubic symmetry. And the second one, it's a chiral structure. So it has a handedness associated with it. If you have those two properties, what John Pendry predicted quite a few years ago is that what you can do if you make it as a metamaterial, that means the screen channels that you've seen of the gyroid, they're made out of metal, freestanding in air, for example. Then if you have those two properties, what you have is an optical band structure that looks a little bit like that. Just a little bit of introduction. If you're not familiar looking at these pictures, on the x-axis, you have the wave number, which is basically the frequency in space. On the y-axis, you have the actual frequency in time. And then you have a band structure or a dispersion relation, which relates the two to each other. Especially, I'd like to draw your attention to those two bands because those are the ones that I'll be talking about. And I'd be going a bit more into detail about what this is, what I'm getting at. First of all, let me introduce you to negative refraction, because that was what my collaborators, my experimental collaborators, were after when they were looking at these gyroid materials. So what John Pendry predicted basically is that you can get negative refraction through these specific band structure. What's cool about negative refraction? So this is an animation of a pool. Sorry for the image quality, it's really bad. This is if you had normal water. This is how you would see note the ground of the pool here. This is what you'd see with a normal liquid. If you had a negatively refracting liquid, this is what you would see. And the cool thing about this is you're basically standing here on the side of the pool and you're seeing the walls inside the pool. So it's bending light over. You see in there like that, which is, well, in itself an interesting effect. So what can you do with it? So two things you can.
Just looking at it for a second.
It's good.
It's seasick looking at the pool.
Oh, you're still seasick. Okay. So sorry, I only have half an hour. I still have to continue. So one of the things that you can do is a bit more, well, not really scientific, but in principle, for one particular frequency, you can make an invisibility cloak. Okay, that's more a selling point. The second thing that you can do is maybe a bit more scientifically interesting in the end. You can make a perfect lens with this negative refraction. And there's some downsides to it. It's not, I mean, you have to image in the near field and it's not applicable everywhere, but I'm a theoretician, I'm not a salesman apparently. But in principle, you can build this perfect lens. But what I mean by this is with an ordinary lens, you're always diffraction limited. So if you want to create an image with light of, say, 600 nanometers, then roughly the focal spot size that you can get down to is 300 nanometers, half of that. Here you can go down to 1 nanometer below, whatever you want in theory. That is basically why this is such a bit of a holy grail, why you want to have it. Now, how do you get it? So this is the picture that usually people in the metamaterials community are looking at. So natural materials, here dielectrics, like glass, wood, whatever, any biomatter, basically, that has a positive permittivity. This is how light, the electric part gets manipulated by a material, and a positive permeability that's on the y-axis. This is how the magnetic field gets modulated. And for dielectric, you have both of them positive. Then you have a single negative medium up here on the left-hand side, which is typically plasmonic metal. So these are natural materials, these exist. Then here it becomes a bit more exotic. There are ferrites, okay, at certain frequencies, not at optical frequencies, this exists as well. What doesn't exist in nature is epsilon and mu both being negative. And that is essentially what the promise would be of such a metamaterial, and that is essentially what leads to this negative refraction. I don't have to talk about this much because we've heard about this before. So this is my physicist's way of showing tri-block polymers, and here's a diblock. Here's a phase diagram. On the x-axis, you have volume field fraction. On the y-axis, you have the chi parameter, which is essentially inverse temperatures or some. And then you have phase diagram, and you can get multiple structures. We're interested in the gyroid. It's up here. It's in this phase diagram, but it's here labeled a little bit different. Q200. No, where is it? Yeah, it's here. It's here. It's a very small phase pocket. Anyways, how do we make this as a plasmonic metal? Because this is what I promised you would lead to the negative refraction. Well, we start with a surface sample thing. This is A here. Forget about this. This is just, I've just been lazy. I go this way. You then use some, either you put it on an electrically conducting substrate or use something like atomic layer deposition in order to make it electrically conducting. Once you have that, you use electrochemistry. There is a cathode, you put a voltage on it, and then you plate, electroplate basically gold into the channels. And then you have your metamaterial after using some chemistry to get rid of the remaining bulk. It's another way of looking at the, so here you have the gyroid made out of gold. I want you to note that lattice constant is roughly, we're in this ballpark, 15 nanometers, so it's pretty small. And what you see up here, this is the actual experimental thing under TEM and SEM, sorry. And this is an optical micrograph. So you see it shines kind of red. I'm coming to that. So let me get back to John Henry's prediction. Here's John Henry's band structure, and what the band structure itself doesn't tell you is that these bands are basically what you have normally is this parabola of bands that go out of k equal to 0, which is called the gamma point, and they are by the chirality. What the chirality does is they are double degenerate. It pulls them apart in both directions. So you have one band on the right hand side and one on the left hand side. And what happens then at this x, those bands couple only to LCP, left circular polarization. You can imagine, because it's chiral and left and right circular polarization are chiral, this is roughly where this comes about. And this is kind of where you get a selection as well. If you go in with LCP light, then you're only going to select, if you're going along this way in your propagation direction in the material, you're only going to select this mode. And this is another way of looking at negative refraction. It's a so-called left-handed propagation. What that means is you're here in this frequency region, you're in a region where you're propagating forward. So the energy, you're not propagating forward. The energy propagation velocity is pointing towards you, is going to the left. And this is basically because it's given by the slope of the band structure. Whereas the phase velocity is going in the positive direction. This is basically k over omega. So what you have is you have phase and energy propagation velocities are counter-propagating. And this is basically, if you look at it on a board, I don't have time for this, you can easily figure out that this automatically leads to the negative refraction shown. Now comes the bummer in my talk. This is what my theoretical colleagues at Imperial College have calculated. So the drawing apart of the bands, you see here blue LCP, red RCP, same color coding, it doesn't really happen. So the two bands are essentially staying on top of each other. This is in the what they've simulated. This is what they got from an analytical calculation, the dashed lines down here. And there the splitting apart happens, but what they did, they cheated. So they basically, this intertwining, this full network geometry of the gyroid, they approximated basically by 3 helices going in 3 Cartesian directions of space. And for the 3 helices, you see the splitting. And the splitting comes from the fact because you basically, what the light does, it excites currents along these helices, and it excites them, of course, differently whether you have LCP or RCP polarization. Now, this is what I did. This looks, here I've taken the full network into account. Let me talk you through this because this looks a bit complicated, maybe if you look at it for the first time. So what I've done is I've taken the underlying SRS network of the gyroid, and I've mapped it to a 2D plane so that you can even more easily color it and see it. So basically, what you have is here you have the nodes of the network in one unit cell. And the blue things are the edges. And please forget about the arrows. This is just for labeling. So blue are the edges, and the X in this plane, X and Y, you have exactly the geometric representation of the network here itself. The Z coordinate is in the nodes. So what you have in the gyroid is you indeed have helical features. For example, you have this square-shaped helix here going down, which goes from 3 to 1 to -1 to -3. So you have a helix that winds down like that. But at the same time, you have a bigger helix that winds down in the opposite direction, which goes from, this is an octahedron. So if you continue here along this path, the unit cell, then this one goes over here and continues here. So you have them interconnected, and you have no possibility to run one of those helical patterns without the other. So whatever happens in here, when I have something going down, a current going down this right winding helix down there, then I automatically have a current by the same amount that goes down the left winding helix, the bigger helix. And in the metamaterial picture, where we are, just as a reminder, I said my unit cell is 65 nanometers, where we're in a homogenization regime. So the light basically sees an average over the whole unit cell. Those two cancel each other out. And that is essentially why if you do the real thing, if you simulate it, or if you do the real modeling, you don't see them getting apart. So here's what I got for my model, and I approximated quite a bit here. So what I said, for example, is that if I go along these edges of the SRS network, I have it's a tube around there, and I have one current that flows down there, and it's basically more or less within the strut. It doesn't change a lot. Oh, sorry, my fault. The story goes a little bit different. Okay, I forgot about this slide. So what I like to, this is experimental evidence, what you see here, and I'd like to mention two things. First, this is reflectance that they measure. So they have a sample of this metamaterial, and they shine light upon it. And this time it's linear polarized light. So you have reflectance here, and it's logarithmic scale. So this is experimental data. Here you have wavelengths, so you need to turn your head a little bit around when you're comparing this to the band structure. So it's basically lying flat here now. So here you don't have modes in the material, so it makes sense that you have a high reflectivity here. It's basically reflected. Here, you do have nodes, so a lot of light goes in. But I'm talking about linear polarization, and this is what this compass rose is about. So we have a color coding here between the different directions of where the electric field is putting inside the plane of this. This is the termination plane of my structure, light comes here from the front, from you. But it's polarized in different ways. And you can see that there's a very broadband effect where you have a distinct separation between the different, note that this is again, this is a logarithmic scale. You have a distinct separation between the different polarizations. And this for a cubic structure would be totally unexpected. So I'd like to summarize, we haven't found the negative refraction that we were after, but instead we found some very distinct polarization effects that weren't expected from the bulk theory. So this is again what I got after simplifying my model quite a bit. You get a very simple expression for an effective permittivity, how you can model the full material. So it behaves like an homogeneous material, and this is completely polarization insensitive, and is actually just a volume average, basically, over the permittivities of the base materials that you put in. This is the dielectric background, this is the gold filament, and you just average over them. The only thing that you need to do, and this is a dimensionality effect, is that the real volume field fraction, which I labeled phi here, needs to be divided by 3 in order to get the right result. And by that, if you plug that back into Maxwell's equations, what you get is a very simple solution that looks very similar to that one. So you have the twofold degeneracy up here, these are blue and red. You have flat band in first order. I mean, it's bending upwards here, but close to the gamma point, it's the same. And you have an evanescent solution, which means it doesn't pop up in this diagram here, where waves are not propagating into the material. So this is a very, very simplified theory, but it covers the main physics, and it gives you the right point in frequency for this here. We're ending up here and not there. So this is great, but how then can you explain this linear dichroism? How am I running time?
5 minutes.
5 minutes. Okay, that's great. So, and this is a little bit of geometry and topology, which I promised. It's a surface effect. When I say topology, I really mean just real space topology, network topology, in the sense of how it's connected. So really basic. This is a 110 inclination of that crystal. If I cut that crystal at different planes in the unit cell, I'm going to see different patterns. And the important thing about this is, in the bulk, as I've said, you would expect no discrimination between the polarization states. But at the surface, what you have here is you have these intrusions or islands that stick out. And these can be easily polarized. Here, if you do it like that, they look more or less isotropic, and there you wouldn't expect much in terms of polarization sensitivity. But here they are strongly anisotropic, and they are also coupled here because they are basically in a chain. And we can't guess, these are simulation results, and what I show here is the reflectance at one particular wavelength at 650 nanometers, just to demonstrate this. And here we've quantified the termination from one parameter 0 to 0.5 within the unit cell, which basically samples the whole unit cell in that direction. And what you can see is different patterns. So here you have currents can flow freely in 2 directions, independent directions. And what you then would expect is that you don't get a strong polarization sensitivity, and that indeed that's what we measure. That's what we simulate. For this, you have tiny nanogaps here, so currents can flow freely in this direction, but you have like little antennas in the direction perpendicular to that, and indeed it pops up as a resonance. If you go here, you have what I've shown before on the left-hand side. You have these small islands which are highly anisotropic. Again, it shows up as a resonance. Here you have isotropic islands. It doesn't do much again. And of course, in the experimental sample, you would expect to see an average of those effects clear. This is an idealization. So we did a little bit of an additional analytical modeling to that. So what I did is, what if we think about these termination planes as a material, as a thin material themselves, and then trying to apply some, this is a more than 100-year-old theory, it's called Maxwell-Garnett. So you basically just, you're taking these and you're coming up with an effective homogenized response of that material yet again, except here we make it really very thin on top of the bulk material that where I also have an analytical formula for. What is astonishing is that if you take these islands, what you have as this is the effective permittivity that you get when you polarize around this blue arrow and when you polarize around the red arrow. And what you see is that along the blue arrow, it acts like a dielectric. It's pretty boring, it's pretty flat, and it's on the order of 2 or something. If you're along the red direction, you have a super strong resonance. And this makes it possible that even though this is very thin, you get a very distinct different signal between the two. So if we compare this model where I said, okay, we have this thin surface and we don't have any touch parameters in there. The thickness of the surface is simply given by the geometry of the material itself. So this is full self-consistent within itself. It's roughly 8 nanometers. What you get is the simulation results that we got for the full wave modeling of the structure are the solid lines, and the analytical theoretical results are the dashed lines, and you see qualitatively they match extremely well, even though we've approximated quite a bit. And with that, I think my time's up more or less. I'd like to thank you for your attention.
Yeah, that's very, very interesting. I'm just wondering whether you have considered other network interfaces, like the double diamond, etc.
In fact, for this work, we haven't, because this was basically really experimentally driven. They found this in experiment and they were puzzled where this could come from. And I've talked with James and we thought about different things, and then we found it's a surface effect. It is thought, I mean, it's intrinsic to any kind of 3D network, I would say. What you have to do, if you take a simple Cartesian network, of course, if you cut that along the 100 plane, then you're just cutting straight through the wires, and then nothing would happen, of course, because then you have but if you do it at any oblique angle, similar effects would happen. And this is intrinsic to any percolating material where you have a network-like material inside. If you have a typical, other metamaterials are made out of meta-atoms, often where people just consider small metallic objects and they put them on an array. There it doesn't matter too much. But for these percolating network-like structures, I think for all of them, you find similar effects.
Just see if I get the top line summary on this result. Like, so the prediction for negative refraction for level set models of gyroid, that's not true.
Exactly, for the gyroid, it's just not true, and I think I understand why.
For any field fraction, for any
exactly.
So
I mean, well, I mean, what the assumption behind this is that you're in the homogenization limit, which means, or at least, I mean, the assumption is that both the scale of the wave number and of the frequency are much smaller than the. I mean, if you invert it, much smaller than the wavelengths of the light that you're interested in.
If you had parallel helices, it would be.
Yeah, then it cancels out. Yeah. But if you have what I call a plasmonic crystal, so if you have something that is made out of metal, but the metal is structured on the order of the wavelengths of light, like in a photonic crystal, this would change.
Okay.
Then this wouldn't be true anymore.
Okay, let's thank our speaker again.